Okay. The topic that we are going to study today is complex numbers. Now, what is a complex number? Actually, let's start from time way back in times. At some point way back in time, basically, we started developing numbers very early. For example, at the moment some people or some group of people started to learn how to count, they virtually developed a set of counting numbers or natural numbers. Then time progressed and we were able to develop the idea of negative numbers. So humankind actually discovered a bigger set of numbers, which is the set of integers. And I use the term discovered, but the more appropriate term should be invented, because technically numbers, we cannot see numbers here and there, right? We can realize a number when we can relate it to something. For example, if you have two pens, you can count pen number 1 and pen number 2. The numbers themselves do not exist anywhere, but you can relate them to the idea of counting. Only then you can realize counting numbers, right? Similarly, technically, these are our inventions in a way. So time progressed further and we were able to start dividing numbers. And when we started dividing, we have seen that some numbers are not entirely divisible by some other numbers. So the idea of rational numbers were introduced. Fast forward a few more years, probably a few thousand, and there were people in Greece who were able to find some numbers that are not part of this set yet. For example, numbers representing hypotenuse of a right angle triangle with base and opposite equal to both 1. So that number is √2, which does not belong anywhere in this set. So we incorporated those as well to develop a superior set, which are called set of, the numbers in this set are called real numbers, right? And actually, this does not stop here. We progressed further and developed a bigger set of numbers called the set of complex numbers. Now, basically, what is a complex number? If you try to solve an equation that looks like this, it's easy to solve. X equals to plus minus 1. But once you have something like this, up to the point where we were still not able to develop the idea of complex numbers, we could not solve such problems. But then we actually, technically, each of these are extensions to the predecessors, right? So we just extended the set of real numbers to a big, newer and bigger idea so that we can actually include solutions of these newer kind, actually. And what we do is represent this guy √-1 by a symbol I, so that x can be written as plus minus 2i. So if you square this number, both I and 2i and minus 2i, you get 4i square, and simply I square is minus 1. So up to this point, this is just a symbol, but later we will find out that this is way more than that. So there can be numbers, for example, x squared plus 4x plus 3 equal to 0. If you solve this problem, what you get is x equals to minus 4 plus minus √16 minus 4 times 1 times 3, so 12 by 2. So minus 4 plus minus √, I think I wanted to write 5, but I wrote 3 mistakenly. So if I write 5, then I have to write not minus 12, but minus 20 here. So we have minus 4 here. So if you divide, if you express root over minus 1 by I, you have plus minus 2I divided by 2. So minus 2 plus minus I. So if you start using this symbol more frequently, you will you'll be able to find out that there are numbers not exactly of this form, but probably a combination of real numbers and these guys. So the overall structure may look like something like this, where A and B are real numbers. I is something new, something special. Now, in mathematics, if you start taking level 3 courses, you will encounter a course naming abstract algebra. In some ways, this course, along with linear algebra, is basically a foundation to study abstract algebra in some ways. So in abstract algebra, you are going to study a special kind of set of numbers called field. Field is basically those set of numbers where all 4 operations, addition, subtraction, multiplication, and division are defined. All defined in field. By define, what I mean, for example, if you choose the set of integers, you will you are not always capable of subtracting. For example, you cannot subtract 7 from 2 because it would give you -5, and -5 is not a part of the natural numbers. So if the world is limited to natural numbers only, in that world subtraction would be difficult. It would be actually undefined sometimes. For example, even if you include the negative numbers, for example, set of integers, you are not going to be able to divide here, because even though 4 by 2 or 6 by 2 is both integers, but sometimes you may encounter a situation where you want to divide 3 by 2, and what you get is a fraction which is not a part of the set Z. So if the world is limited to fractions only, dividing 3 by 2 is not going to happen there, right? That's going to be undefined there. But in the set of rational numbers, you are not going to be limited to any limitations doing any of these 4 calculations. So technically, N and Z are not field, but Q is. In fact, R is also a field, and I'm adding to that, the set of complex numbers is also a field. You can add, subtract, multiply, and divide in this set. How we do that? It's just customary to express complex variables by Z. That is, in case of real numbers, our favorite choice of variables are mostly X, Y, etc. In case of complex number, somehow Z is a more common choice. So let Z1 and Z2 be 2 complex numbers from the set of complex numbers. I did not really define the term complex numbers. These numbers are called complex numbers. And sometimes numbers of this form, particularly IB, are called imaginary numbers or purely imaginary numbers. Even though this term is pretty misleading, because the numbers are not really imaginary, they actually exist as much as the real numbers exist. Because as I have said earlier, a number exists only if you can relate it to something existing. Otherwise, numbers do not fly around in our environment, right? So if you can realize the number 2 by counting 2 pence, you are going to just say that the number 2 exists. In the same manner, if you can realize any physical object or any physical idea using the number 5i, you have to admit that 5i exists. And actually that happens. If you take circuit courses as, I don't know, optional or something, you'd see that in electronics courses, Imaginary numbers actually play a vital role, especially in circuits that involves inductor and capacitor. I don't think, okay, I was about to say that I am not interested in getting deeper into those, but let's just use that. We have time, right? So let's just use that time to explore some ideas. For example, this is borrowed from physics and electronics, actually. If you compare the two elements I drew here, the one above is called a resistor, and the current through it and the voltage across it are related by the equation V equals to IR. Or in other words, V by I is a constant. We call this constant a resistance. And this law is a well-known law, right? Ohm's law. If you want to do something similar treatment with the one below, if the current through it is I, the voltage across it is V, and this is a coil of wire, actually, generally called an inductor. The current voltage relationship between the relation between current and voltage of an inductor is not something like this, but rather this. V is equal to some proportionality constant L di by dt. This comes from the Lenz experiment, the famous Lenz experiment. If you have a coil of wires and if you take a magnet, and if you somehow take this magnet, move this magnet around this coil, you are going to observe current passing through the circuit, which do not really have any voltage source. So basically, there is going to be voltage induced across the inductor, and that voltage is proportional to the number of flux lines that passes through the coils per unit time. So the rate of change of flux lines with respect to time. So what we do is use a proportionality constant L, and this L is called the inductance of this circuit material. Now, inductance can be defined the same way you just define other constants in physics. You just apply the idea that if this guy is 1 and this guy is 1 volt, then the value L has is 1 Henry. So the unit for L is Henry. Now, this value phi is actually proportional to I. And if let's not use the exact expression L already. So let's keep it in the proportionality form. Now phi is now again proportional to I. So applying this, you get V is proportional to di by dt. And then let's introduce the idea of L and define it and define its unit and so on. So that is how the relation between voltage and current through and across, across and through an inductor is established. Now, this relation suggests that V by I is not a constant in this circuit. Circuits of this form are generally called, if I'm not wrong, they are called active circuits as far as I can remember. I'm not sure. The name does not matter. Anyway, not ohmic circuit. That would do for us for now. This kind of circuits are not ohmic circuits, but circuits involving resistors only are ohmic circuits. Similar can be said for capacitance. If the current through is I, the voltage across is V, they have a relation which can be developed in similar manner, is from physics, of course. I is equal to C dV by dt. So V is just 1 over C integral of I dt within a suitable limit, probably from 0 to t. So in case of an inductor, you have to differentiate current to get voltage. In case of a capacitor, you have to integrate current to get voltage. So This is a resistor. This is an inductor. And we have a capacitor here. So where does I come in here? Let's see. If you have studied some physics, then you should know that in most methods that we use to produce electricity actually involves some sort of rotation, right? For example, in Kaptai hydroelectricity, what we do is we build a dam, and from the dam, we basically, water falls from a very high, what do we call the high altitude, sorry. And there is some object that kind of looks like a fan, which is called a turbine. When water passes very fast through this turbine actually rotates because the blades are made in a similar manner that we can see in our electric fans, right? So using this rotation, electricity is produced. Where does rotation come in the principle of producing electricity? Let's see how. If you have, let's not draw the 3D view, but okay, let's draw, excuse me. If you have a coil, a single loop coil of wire, and you have North Pole and South Pole here, then magnetic flux passes through the coil. Now, if you apply current through the coil using some method, what happens is this current faces a force that is caused by the magnetic flux, which has the expression F is equal to I L cross B, where B is the magnetic flux and L is the length of the coil. But the coil has actually 4 parts, and the parts which are almost horizontal here do not feel actually any force of this sort, because this part and this part are aligned with the magnetic field. But the longer 2 sides actually encounter forces. But if you apply the thumb rule, you will see that one side realizes force in one direction and the other side in the other direction. I don't know if I showed the direction correctly. It may be the exact opposite of what I should have drawn, but that doesn't matter. What matters is the directions are opposite and equal. So the coil actually encounters a rotational motion, and when it rotates, at some point, if this is North Pole and this is South Pole, at some point the coil in full face the lines. But at other points, while rotating, the coil becomes something like this. So the number of flux lines through the coil actually reduces, and at some point it becomes completely flat. So the number of flux lines through the coil is actually 0. So we denote the number of flux lines by phi, right? So this expression of phi is actually varying while the coil is rotating, and the expression should be something like this if omega is a frequency of rotation of the coil. So the variation suggests a cosine or sinusoidal idea, right? And if you actually do some calculations, for example, the overall full phase area, say for example, is A naught, then at any moment the area is actually A naught cos omega t. Basically, cos theta, if for example this is the flux line and this is the coil surface of the coil, and if this angle is theta, then if for example at the beginning, if the coil was in this dotted line situation, consider that position theta equals to 0, then after some time t, the coil is here now. The angular distance covered is considered to be theta, for example. Then the flux line originally were covering this entire zone is now being able to cover this portion of the zone only, and it's missing the parts here and here. There are flux lines through these part as well, but they are not actually crossing the loop. That is why the loop is the loop can get actually a portion of the overall number of flux lines only, and that portion is actually proportional, should be proportional to this length, right? And this length by this length is cos theta, because this is theta. So if this length is proportional to the area as well, so if this is A and if this is A naught proportional to, of course, then A by A naught is cos theta. And what is theta? Theta is the angular distance covered, which should be equal to omega t, where omega is the angular frequency. So A is equal to A naught cos omega t. So phi, which has this expression A times B, where B is the magnetic flux, the magnetic field, should be something like A naught B cos omega t. Consider this A naught B to be the max value of phi to get an expression like phi naught cos omega t. So basically what we do while producing electricity is reverse this principle. We put a coil, a big coil or a number of coils probably inside some place where a magnetic flux, number of magnetic flux lines are passing through. Then we somehow mechanically rotate that coil so that electricity is induced in the spot, that coil in the opposite direction to negate the entire action, right? This is the idea from Lenz. So that is why we actually see that whenever there is an electricity plant, whatever method they are using, maybe it's a nuclear plant, at some point they are actually rotating something. In nuclear power plants, what they do is, using nuclear fission reaction, they vaporize water, and that vapor passes through a coil very fast to make rotation. So somehow mechanical rotation is involved, right? And since mechanical rotation is involved, if you can see that phi has a cosine expression here. So if you somehow find the phi is proportional to I, right? And if you somehow, let's use another page. If you somehow, since phi and I are proportional, I must have a sinusoidal. I could just write cosine, but let me write sine. Sinusoidal expression of this kind. Then for an inductor, V is L di by dt, which means L times derivative of I naught sine omega t. So we get I naught omega cosine omega t. Let's call this guy just V naught, because why not? It is the amplitude of the voltage, right? So V naught. Now cosine omega t can be written as sine omega t plus pi by 2. So you can see that I and I naught, apart from the magnitude, just we are not interested in the magnitude actually. We're interested in the phase angle only. So the phase angle difference between voltage and current is actually pi. They are basically almost the same expression, only differed by, excuse me, an angle pi by 2, 90 degree. So what happens here is the voltage, in terms of angular phase, the voltage leads the current by 90 degree. And if you do the same analysis for capacitors, you can see that the voltage expression is actually integral of I. So eventually you would get a similar expression, only that time, since we are integrating, integration of sine is minus cos, there is a negative number involved. So at that, in that calculation, you would get a minus sign here, not pi by 2, but minus pi by 2. So this is for inductors. And for capacitors, voltage not leads but lags current by 90 degrees. Now, let's stop learning physics here for now, and let's get back to complex numbers so that I can explain why imaginary numbers are not really imaginary. We are going to get back to this point probably within 5 or 10 minutes. As I was saying, complex number set is actually by definition a field where all 4 operations are defined. So if we have 2 numbers Z1, Z2 from the set of complex numbers, then probably Z1 has the expression a real part and an imaginary part, and Z2 maybe has an expression x2 plus iy2, because we have shown that we have argued that complex numbers are of this form, right? Then we can define the addition like this. Initially, it's x1 plus iy1 and x2 plus iy2. But what we can do is add the real parts and the imaginary parts separately to get x1 plus x2 plus y1 plus y2. And we can generally, this guy is called real part of Z1, and not iy1, but only y1 is called imaginary part of Z1. These 2 notations are standard notations in study of complex numbers. So this relation can be stated as what we just wrote. It can be stated as real part of Z1 plus Z2 is just real part of Z1 plus real part of Z2, and real part of Z1 minus Z2 is just real part of Z1 minus real part of Z2. We can, because we can just define subtraction in a similar manner, Z1 minus Z2 is, if you do same operation, just a minus comes here. So we would get eventually x1 minus x2 plus I times y1 minus y2. So 2 of the 4 basic arithmetic operations are already defined. Let's see how multiplication is defined. Z1, Z2 is x1 plus iy1 and x2 plus iy2. So we are multiplying 2 complex numbers, and we have seen our argument involved the idea that if you divide one member by another, if you multiply 2 members from a set, that product may or may not belong to that set, and accordingly we decide that multiplication is defined or not defined in that set. We are not yet sure if multiplication in set of complex numbers is defined, but all depends on the outcome, if this outcome is in the form a plus ib or not. Let's see. If you multiply term by term x1, x2 plus I x1 y2, so I multiplied by x1 this guy first and then this guy. It's I y1's term now, so I y1 x2 plus I y1 y2, but we have 2 i's here, so I1 square, and you should be able to recall that I square is -1. So this makes this part a real number. So we can separate the real numbers like this and take I as a common factor to write the other 2 terms like this, x1 y2 plus y1 x2. So this is indeed in the form a plus ib. So the product belongs to the set of complex numbers. Remaining is basically division. So basically, before actually defining the division, let us define another term which is called complex conjugate of a complex number z equals to x plus iy, and it is denoted by z bar. Its conjugate, any conjugate of any complex number z is denoted by z bar, and it is actually the number where you replace I by minus I, and that's nothing else. So if you have a complex number like this, if you multiply by the conjugate of the number in the denominator on both numerator and denominator, what happens is multiplication of a number by its conjugate gives a very interesting output. If you multiply x plus iy by x minus iy, even though both of them are complex numbers, what you get eventually is x square minus I square y square, which is equal to x square plus y square, because I square is -1. So this is actually a real number. So eventually you would get x square plus y square in the denominator and x minus iy in the numerator. This is actually of the form a plus ib. X, you can just write x by x square plus y square plus I times negative y by x square plus y square. So this is of the form a plus ib, so it must belong to the set of complex numbers. Even z times z bar belongs to set of complex numbers, because as we have seen, R is nothing but a subset of C. That is basically every real number a is actually a plus I into 0. And every real number is a special case of a complex number, right? Anyway, so this is how we define the multiplicative inverse of a complex number, so that whenever you have two complex numbers, z1 and z2, and you divide one by the other, what you get is z1 times 1 over z2, and we have seen how reciprocal of any complex number is another complex number. So this division eventually becomes multiplication of complex numbers. So the overall result turns out to be something of the form a plus ib, as we have seen in number 3. So division of complex numbers is also defined. Now, we are interested in representing complex number geometrically, just like we represent real numbers using a line where the midpoint is 0 and any number 3 is here, -3 is here, and so on. Every real number has some point, has some position in the real line. Similarly, we want to develop an analogous idea for complex numbers. So we need to draw some geometric line or plane or anything where we can find every complex number that exists on Earth. So how we can do that is dependent on the fact that complex number actually, even though a complex variable is a single variable, it actually has two parts. And you cannot put the two parts in the same line. To visualize them separately, we have to use two different lines, which would actually produce a plane, right? So if we call this the real axis and if we call this the imaginary axis, we can develop a method to put every complex number in this complex plane. It's called a complex plane, or it has another name, Argand plane, if I have not made any mistake writing the spelling. Anyway, so here is how we put any number. First of all, try to realize that all the numbers in the real line is real numbers. For example, you have 3 here, you have -3 here. But if you want to put 3i, the purely imaginary numbers, you have the y-like axis. It's not really y-axis, it's the imaginary axis. So you have this y-axis like axis here to put 3i here and -3i here. Now here is an interesting idea. Basically, when you should be able to realize that these two axis system must produce something, some ideas that are more interesting than representing real numbers in the real line. And here is the first one. If you multiply 3 by the number I, you get 3i. Geometrically, you are getting 3i from 3 by a rotation of 90 degrees. And let's verify this fact for the other multiplication as well. If you multiply 3i by I, you get 3i squared, which is -3. If you multiply -3 by I again, you get -3i. And if you multiply minus 3i by I again, you get minus 3i square, which is I. So technically, I can be thought of an operator that rotates any complex number in the complex plane by 90 degrees. So in this, using this fact, we can put any number, for example, 3 plus 4i in the complex plane. So let's see how we place 3 plus 4i in the plane. Sorry. Okay, so you go 3 place to the right because you want to place 3 here. Then you have plus 4. If you just had plus 4, you have to go 4 more steps to reach here. But we do not really have 4. We know how to place an additional 4 steps in the real line, but we have to step additional 4i steps. So I is applied to 4 only, not 3 plus 4 overall. So that is why this part is rotated 90 degree. So this must be the 4i part. So this point must be 3 plus 4i. So this is how we place a number. Some people prefer to think like this. We get 3 plus to the right, then 4 plus towards north to get 3 plus 4i. But the original idea is actually this. Okay, now let's get back to our physics part. We have already seen that I has this role that it rotates any guy in the complex plane by 90 degree. We can see similar ideas in case of inductors and capacitors also. So in case of inductors, voltage leads current by 90 degree, as if you have voltage in the numerator and current in the denominator, then what you get is not a pure real number, but an imaginary number. Because this kind of, if you express this current and voltage using complex numbers, then this makes perfect sense, because voltage is actually adding 90 degree additional phase to current when you get the expression of voltage from current, right? So technically voltage is just some pure imaginary number times current, so that after multiplication the voltage is something that has 90 degree more phase angle than current has. And in case of capacitor, the voltage by current relation is it's 90 degree clockwise rotation in the negative direction, right? So you have a purely imaginary negative number. Now what we do is, for inductor we write subscripts like this, and for capacitor we write subscript like this to make more sense and distinguish between them. And in circuits that has both resistors and capacitors, which are basically every circuit in practical world, the overall voltage by current relation is generally something like a real part plus an imaginary part, or something like this. So basically voltage by currents are generally complex numbers. So this kind of resistance like object, which are not really resistance, are called impedance. And so you can see that many of the courses of electrical engineering are going to involve complex numbers, because the circuits are involved with complex numbers pretty early, right? This is pretty early background fundamental ideas of electrical engineering. So you can see calculations of using complex numbers and variables all the time while studying electrical engineering courses. So we could relate I to something physical, just like we could relate the number 2 to 2 pence while counting. So imaginary numbers are not really imaginary, they actually exist equal as much as real numbers exist. Anyway, let's get back to our discussion. So we have defined all four operations of complex, all four binary arithmetic operations of complex numbers. Now, let's see another kind of representation of complex numbers, which is the polar form. Before describing the polar form, let's define, for example, this is a complex number x plus iy. We define two new terms. One is modulus, which is not really new. If this is a complex number z, then this is the modulus of z, which this is a distance from the origin to this number. And as you have seen, this length should be x, this length should be y. So this length should be root over x square plus y square according to Pythagoras. So modulus is an old term we are reusing from real number lecture, right? This is actually the distance from the origin of our complex number. We define another term, which is this angle. Theta is the angle that our radius vector, this line is called the radius vector, corresponding to our complex number. So theta is the line that our radius vector makes with the positive real axis. So this guy is called modulus of our complex number, and this guy is called argument of our complex number. And for some reason, in the old books, I have no idea why, this is alternately called as amplitude of z, which makes no sense to me because amplitude actually resonates more with the term modulus. So if this was alternately called amplitude, I would be okay with it. But somehow, I don't know why, argument used to be called amplitude. Argument was usually called amplitude in the old books. And same you can see in the book by Barnard and Child. They called argument of z. This is argument is represented by generally arg z in modern texts, but in Barnard and Child they actually write mz, something like this. So whenever you encounter this notation while solving exercise problems, do not get confused. They actually means argument. Now, while if I give you a complex number, for example, 1 plus root 3i, if this is z, you can easily calculate its modulus. This is just 1 plus 3, which is 2. And you can easily calculate the argument of z, which should have the expression. You can see that y by x is tan theta, right? So theta must be tan inverse y by x. So argument of z must be tan inverse root 3 by 1, which is just 60 degree. 60 degrees, so pi by 3 radians, right? But if another complex number z1 is introduced, which is, for example, minus 1 plus root 3i, then of course it has the same magnitude, I mean same modulus, but what about its argument? Or in fact, let's make it more confusing by writing a minus here. So argument should be, according to the formula we developed, minus root 3 by minus 1, which is exactly tan inverse root 3, and which is exactly pi by 3, which does not sound right, because if, let's see graphically, if 1 plus root 3 is somewhere here, 1 plus root 3i, then minus 1 minus root 3i should be somewhere here. So if I just add this radius vector and this one, for 1 plus root 3i, the argument is this angle theta. For 1 minus root 3i, according to the definition of argument, we must have this angle, which is actually 180 plus this sin theta. Let's call it theta 1, and we can see the relation theta 1 is actually 180 degree plus theta. So instead of pi by 3, it should be pi by 3 plus pi, which is 4 pi by 3. And this one is correct. Pi by 3 is not. But that means this formula is applicable only for first quadrant. So while dealing with numbers in the other 3 quadrants, you have to examine every time manually to see where that number belongs and what the argument should be. And you have to think every time pretty carefully while calculating the argument. All right. So if it is in the second quadrant, generally it's 180 minus theta. And if it's in the fourth quadrant, it's either minus theta or it's 360 minus theta. So please do, this one is for the third quadrant numbers, right? Please do similar calculations on your own for second and fourth quadrants and develop expressions. And while solving problems, you do not have to remember formulas. You can just geometrically calculate argument every time for every number individually, right? Okay. Sometimes you would see that basically you have experience with polar coordinate system. So if this number is x plus iy, then geometrically this is x, this is y. Let's call the modulus r for convenience, and let's call the argument theta. Then this is pretty analogous to what we learned in polar coordinate system. So according to that knowledge, x is just r cos theta and y is just r sin theta. So if you now consider the complex number z equals to x plus iy, this can be written as r times cos theta plus I sin theta. Now there is a famous theorem by Euler, who happens to have something to say in every field of mathematics and even outside mathematics, which looks like this: cos theta plus I sin theta. There are many ways you can prove this. There are multiple proofs, but the most straightforward and the most easy to understand for beginners is if you expand this left-hand side in Maclaurin series, expand cos theta in Maclaurin series, expand sin theta in Maclaurin series, and put everyone in this equation, and equate coefficients from both sides, you would see that the coefficients match for every term. So that is how you know that this equation is actually something valid. So if you apply this equation, you would see that we can write any complex number z in this form, r e to the power I theta. Now this form is called, of course, the Cartesian form, because why not? And this form is called the polar form. Sometimes it's called exponential form for the obvious reason that it involves exponential, right? Now, this form is actually pretty helpful. In many cases, we are more comfortable with Cartesian forms. I'm talking about coordinate geometry actually. In coordinate geometry, in most cases, we prefer Cartesian over polar any day. We use polar only when polar makes the calculations way more easier than Cartesian does. But in most cases, even they are of equal difficulty, we prefer Cartesian because we are pretty used to those calculations in Cartesian coordinates. Same happens here also, but sometimes, for example, what happens if you want to find the modulus of Z1 and times Z2? What is the relation between, can we express this guy in terms of modulus of Z1 and modulus of Z2? I mean, modulus of product of two complex numbers can we express that guy in terms of modulus of individual complex numbers? We can actually do that. You can make calculations from here, where we multiplied Z1, Z2, and you can see that we have a real part here. We have an imaginary part here. So you can just take the sum of square and then square root them, which would give you a pretty ugly expression, and simplify that ugly expression to the point where you can clearly see the expression for individual modulus, which are root over x1 square plus y1 square and root over x2 square plus y2 square. Even without doing the calculations, you can understand that the calculations are going to be unnecessarily ugly. But if you use polar form, things are going to be easy. For example, if you just express this guy in the polar form r e to the power I theta 1, and the second guy as r2 e to the power I theta 2, this is multiplication. We have modulus here. So next line, we have something like r1, r2 times e to the power I theta 1 plus theta 2. Now you can see that r was our modulus and theta was our argument. So using that, you can just write modulus of this guy is actually just r1, the guy that's outside of the exponential. That is our modulus. So r1 is just mod of z1, r2 is just modulus of z2. So basically, they are just modulus operator distributes over product of complex numbers. And while doing this calculation, we have already developed, you can see that argument of the product is just theta 1 plus theta 2, which means argument of z1, z2 should be argument of z1 plus argument of z2. So somehow it works like how log operator works. Log of product of two numbers is individually at sum of the log of those two numbers, right? So argument works like log, and it should because it is in the exponent. So it makes perfect sense. Now, similarly, you can understand that. Now let's have a better look at this operator argument. For example, for 1 plus root 3i, let's get back to that guy. So this is the complex number. The argument happens to be pi by 3. But what if someone claims that its argument, the argument of this number is 2 pi plus pi by 3? So argument of 1 plus root 3i, which is clearly, according to our calculation, pi by 3, can also be 2 pi plus pi by 3. They are equivalent angles. And you could just write minus 2 pi plus pi by 3 as well. And you could write infinitely many more of them, because adding and multiplying 2 pi however many times doesn't actually change the angle. All of these are arguments, but which one is the principal argument, the original one, the one we call the leader? Well, you have to apply some condition to the value of theta. You have to apply an interval, call an interval which is the main interval, right? And that interval length should be 2 pi, because the repetition happens after every 2 pi radians. So we call this interval to be our this interval of 2 pi length to be our main interval. And you can understand that pi and minus pi are basically equivalent angles, and that is why you can apply open bracket in any of the side. I prefer to include pi and exclude minus pi. Even including doesn't hurt because they are the same angle. So the main argument, or the leader argument, which we call the principal argument and denote by capital ARG of our angle Z. This has this condition that it is within the interval minus pi to pi. So for any complex number, you will find infinitely many possible arguments, but only one of them is called the principal argument. So sometimes whenever in questions you see a capital here, you should understand that it's the principal one, not just any argument, but the principal argument. Okay, let's move on to our next topic. Let's see how addition and multiplication and subtraction, etc., behaves in the R1 plane. Say this is the radius vector corresponding to the complex number Z1, and this is the radius vector corresponding to the complex number Z2. Where should, this is the real axis, this is the imaginary axis, where should Z1 plus Z2 be? Now, by now you should be able to understand that the complex number behaves kind of like the vectors in R2. For example, in R2, the vectors are like this. In complex number, the numbers are like this. When we add vectors in R2, we add component wise. Similar happens for complex cases as well. So we can kind of treat these guys as vectors, the radius vectors as actually vectors, and shift Z2 here, kind of use the parallelogram law for vectors, and conclude that this guy is actually the radius vector corresponding to Z1 plus Z2. So this point is Z1 plus Z2, and you can do similar treatment for subtraction as well. What happens for multiplication is interesting. For example, if this is Z1, and if this is Z2, let me show you how to find Z1, Z2 here first, and then prove my claim, right? Say this is the number 1. This is the number 1 in the real line. Add 1 and Z1 to complete a triangle O1Z1. Now, for convenience, let me place Z2 closer to Z1 somewhere here. Say this is Z2, and this is its radius. Now, say this is the argument. So this is the argument θ1 for Z1. What we do is rotate Z2 by angle θ1 and extend the radius vector to the length of this guy and complete this triangle. Excuse me. Then I claimed something wrong here. We do not claim that these sides are equal. What we do is, this angle is θ1, of course. Extend this guy so that we can create a triangle. For example, this point, say, let us call this point P, so that we have to extend this green line, the longer green line, to the point P, so that these two triangles are congruent to each other. I mean, similar to each other, not really congruent. Congruent means everything is same. Similar means the sides have same ratio. So we draw this triangle OZ2P in a way so that OZ2P is similar to O1Z1. Z1, the triangle O1, Z1. Then my claim is this point P is actually a representative of the number Z1, Z2. Let me show you why. Basically, this is theta1, right? And what is this guy? This guy is theta2, which is the argument of Z2. So technically, let's use another color for this line so that I can use convenient words to complete my sentences. So the green line has argument theta1 plus theta2. This is the first hint. The green line has argument theta2 plus an additional theta1. So its argument is theta1 plus theta2, first of all. So argument wise, this is Z1, this satisfies the condition for Z1, Z2. That means wherever Z1 times Z2 must be, it must be somewhere in the along the green line. Maybe it should be on at some point on the extension of the blue line. I'm saying green line mistakenly, it's blue line. So the number Z1, Z2 must be somewhere on the blue line, maybe on its extension or something. But all the complex numbers having argument theta1 plus theta2 are situated on this blue line. That is why Z1, Z2 must be somewhere along this length. All we have to now prove is that this length is the modulus of Z1, Z2. If we can do that, we can confirm that P is actually Z1, Z2. Let's see how. If these triangles are similar, then we must have OP by OZ1, ratio of the biggest lengths, equal to OZ2 by O1, ratio of the smallest sides, right? So this means OP, the length we are concerned about, is actually equal to, this is the length of this line is actually 1. So we just have OZ1 times OZ2. These are just modulus of Z1 times modulus of Z2, which is equal to modulus of Z1, Z2, as we have proved earlier. So OP has exact length Z1, Z2, which we demanded, which was demanded for the completion of the proof. So the point P actually represents Z1 times Z2. You can do a similar treatment for division of complex numbers as well. Please let me know if there is any confusion so far in the lecture. Now let's analyze some geometric objects represented by complex equations. For example, let's start with an easy one. Modulus of Z equals to 5. What does this represent in the complex plane? This actually means if Z is X plus IY, this actually means X square plus Y square squared root is 5, which would mean X square plus Y square equals 5 square. So basically, the complex numbers that satisfy this equation are the complex numbers that are situated on the circle drawn in the complex plane centered at the origin with radius 5. So this represents a circle in the complex plane. So this is the equation of a circle in the complex plane. Similarly, basically you should be able to understand that if Z means distance of Z from the origin O, then Z1 minus Z2 modulus should represent distance between the two complex numbers Z1 and Z2 in the complex plane. So if we write something like this, Z minus 2 plus 3i modulus is 5. According to the experience we already gathered, you can do the calculations. Just replace Z by X plus IY and complete the calculation. Eventually, you would get something like this: X minus 2 whole square plus Y minus 3 whole square is 5 square, which should be pretty basic calculations. But even conceptually, you can see that this left-hand side represents distance between all the complex numbers Z from the point 2, 3 in the complex plane. And that distance is kept constant at equal to 5, right? So these complex numbers are the set of complex numbers that are exactly 5 unit distance away from the complex number 2 plus 3i. So basically, since we have 5 as the radius, it should cross the origin, right? So this circle is represented by this equation. So this is also a circle with center at this particular complex number. Basically, you can understand that z minus z naught equals to c is actually a circle with center at z naught and radius equals to c. What should z minus something like this, z minus 10, z plus 10 equals to 20. You can do 3 or 4 pages calculations, worth of calculations, and reach to the conclusion that this particular expression represents something that in geometry we call ellipse. But we can skip the calculation and do some conceptual argument like this. Replace, find minus 10 here and find 10 here. So this guy means distance of our point from 10. So basically, say this is the point, then this is actually modulus of z minus 10. And this is actually modulus of z plus 10. And this sum of these two distances are constant. We have to find the locus of all such points, which keeps this particular sum of distance constant. And this is actually some property that is followed by an ellipse. For any ellipse, if these two guys are the focal points, then distance from any point on ellipse to these focal points, find them and add them, you would get a constant, and that constant is generally 2a. So this is 2a. So the idea is distance from z to focus point number 1 plus distance of z from focus point number 2 is a constant called 2a, which is the length of the major axis of an ellipse. I think for this particular choice of numerical values, it's not going to represent an ellipse because this length is already 20. For the right hand side, we had to choose some number much bigger than 220, maybe write 200 to make sure that the calculations are consistent. So in case of our particular example, 2a is equals to 200, etc. Okay, now let's learn about a very interesting formula called de Moivre's theorem. De Moivre's theorem. Sometimes this is written as Moivre's. The theorem looks like this: cos theta plus I sine theta to the power n is something like cos n theta plus I sine n theta. And it should be pretty straightforward because the left hand side is e to the power I theta whole to the power n, and the right hand side is e to the power I n theta. And there is no reason why you shouldn't be able to see why this is true, right? All right, so we can use this de Moivre's theorem to find complex roots of numbers, but I think I cannot cover that in today's class if I start now. That is why I want to rather let's use the remaining 7 minutes to solve another example. What if you were asked to find the geometric object that is represented by this equation. The ones we used earlier were all involving modulus operator. What if the equation involves argument operator? So let's find out what this particular equation represents in the complex plane. And this would be our last problem. In our next class, we shall start our class by using this theorem to find complex roots of, is it this theorem? All right, at some point it may use this theorem to find complex roots of numbers. So first of all, let's just replace z by x plus iy. Now, well, argument of, let's partition the real and imaginary part, x plus 1 plus iy, x minus 1 plus iy. The problem is, if you want to apply the formula tan inverse y by x, then our argument inside the argument operator has to be of the form a plus ib. At the moment, it is not in that form. That is why we have to use the idea that of multiplication by conjugate on both numerator and denominator, right? So we have argument of, so we are multiplying by the conjugate of what we have in the denominator. Multiplying any complex number with its conjugate gives something like this. We have already seen that. And in the numerator, what we get is, let's write the expression first. X plus 1 plus iy, x minus 1 minus the next line argument. So first multiply these two to get x square minus 1. And then these two minus I square y square, so plus y square. So we already have our real part. The remaining terms are going to be purely imaginary. So first iy times x minus 1. So let's first write I here. In bracket, we have x minus 1 times y. So xy minus y. Then we have x plus 1 times minus y. So minus xy minus y. We have x minus 1 whole square plus s. Let me recheck if I made any calculation mistakes. I times xy minus y minus xy minus, okay. So the xy's gets cancelled. So we have argument of, so we can just write the number like this, x square minus plus y square minus 1 plus I times, we just have minus 2iy divided by x minus 1 whole square plus y square equals to pi. Now, you can understand that I can just write tan inverse. If you divide into two fractions, you can express the overall fraction here in a plus ib form. But a and b would contain the same denominator, which would get cancelled out when we apply the ratio y by x, b by a. So that is why just forget the denominator and just write minus 2y divided by x square plus y square minus 1 equals to pi by 2. Now, we have minus 2y by x square plus y square minus 1 equals to tan pi by 2. But we know that tan pi by 2 is undefined. It is something by 0. So according to that knowledge, we must have x square plus y square minus 1 equals to 0. So in the next line, we can just write that, which represents the unit circle in the complex flow. So the final result is pretty beautiful, right? Okay, I think I should end the meeting with this example. Please let me know if there is any confusion anywhere in today's lecture. Otherwise, I'm just stopping the recording. Okay, let me stop recording and end the meeting for tonight.